Welcome back if you were here for the last session. Welcome if you weren't here for the last session. We had a ton of fun talking about, or at least I did. I don't know if you got to see it, but it was like, it's spiritual for me because it's so exciting. But today, today we're going to talk about how does Intel use different hardware accelerators to make AIPC a reality, right? And in the last session, I mentioned what's driving that. Well, it's obviously these use cases. There's things like voice recognition and recommendation and denoising, which is sort of solved with older technology, right? Those were classic networks that were mostly feed-forward, single-pass inference. But these blue guys have since arisen based on transformers, and that's things like text-to-video and chatbot, chat GPT, voice to music, brain waves to text, text to brain waves. I mean, it's just incredible, the algorithms that have been evolving. So this is clearly driving hardware acceleration. And I also mentioned this last time, if you haven't seen it, the hardware acceleration that's happening today is upon multiple different engines, the NPU, the CPU, and the GPU. And that trend from 2024 to 2025 is not changing very much. It's slightly accelerated on the NPU, 5% additional applications projected in 2025, but about the same on the NPU and a little less on the CPU. What this might cause is a little bit of cognitive dissonance. Cognitive dissonance means that why is this happening? And the truth is that there are multiple different use cases, multiple different profiles of application that are best served by different architectures. In our case, it's the CPU, the GPU, and the NPU. Now, the GPU is unmatched GPU compute. We use it for creator and gamer. Total between the GPU, NPU, and the CPU, we got 120 teraflops. The GPU is delivering 67 teraflops based on XE2 architecture and XMX. I mentioned earlier that I'll be going through the XE2 architecture in detail this afternoon. Spoiler alert, it's used in multiple devices. Okay. The GPU is also paired with the CPU, which is a P-core and an E-core with VNNI, and it delivers 5 TOPS. So think of it as great for quick inferences, low latency things. But the real key here is the new NPU, and I'm going to turn it over to Darren, who is part of our NPU team and the senior principal engineer and architect. So Darren, let's get in there.
Hi, everyone. Thank you. Welcome. I'm Darren Cruz. I work on NPU architecture. Today, I'm going to talk about the latest NPU4 that's in Lunar Lake, delivering up to 48 peak TOPS of performance, over 4x what we had in Meteor Lake, and 2x power efficiency compared to what we had in Meteor Lake. So at Intel, we've actually been working on NPUs for client devices for almost 7 years now. In the beginning, there wasn't, kind of a clear, killer app that we were thinking that there would be on PC. I mean, 7 years ago or so, we were working on more IoT devices for NPU, things like drones, video cameras, security cameras, those kind of things. But it's becoming obvious today that AI is really seeming to permeate all use cases that are going to be on client, from creator to productivity to collaboration. So all these new use cases coming to the client, how are we going to support that? We're going to need more compute, and we're going to need more efficiency. So today, I'm going to talk to you about how we're going to support that with NPU4 in Lunar Lake with our increase in performance and power efficiency. So I mentioned this is our 4th generation NPU. So we've actually been working on NPUs for quite a while. In 2018, we had our first NPU released, NPU1. We called it Myriad X. It was a discrete SoC, again, more targeted to IoT devices. That was only 0.5 peak TOPS of compute. So it's pretty puny by today's standards. But that was actually the NPU that we started integrating on PCs. We first integrated our MCDM driver model that we're using on our current version of Meteor Lake NPU3 and NPU4 in Lunar Lake. We had an NPU2 that was also a discrete SoC called Keem Bay. Keem Bay, we actually started to integrate that in client devices. I think there was 5 PCs last year that shipped with Keem Bay. We were using that for Windows Studio Effects. We worked with Microsoft to enable that. Last year, we introduced Meteor Lake NPU3. That was an 11.5 peak TOPS device. And this year we have NPU4 with 48 peak tops, more than 4x the performance that we were delivering last year in NPU3. So NPU4, it's built on proven foundations. You can expect that all your applications that were running on Meteor Lake are basically going to run with higher power efficiency and higher performance. Okay, so the first question is, how do we scale up the NPU? We went from 11.5 peak tops to 48 peak tops. So we increased the number of engines, just kind of increased the number of raw multipliers. We increased the frequency, about a 40% frequency increase on NPU4 compared to NPU3. And we also improved the architecture. Now we're talking a lot about tops, 48 peak tops for the NPU, 120 platform peak tops. But there's more. It's more than just peak tops that matter. So I actually want to talk about what is a top, and what are the other things in the architecture that matter. So maybe a question like, how many people know what a top is? Anyone? How about how to calculate a top? So we're going to go through that a little bit. So what top means is trillions of operations per second. Usually when we're talking about a top, we're talking about an int8 top. We can also talk about like FP16 teraflops as well. But we're usually talking about int8 tops. Okay, what is an operation? An operation is a multiply and accumulate. So that's basically what we define as an operation. So one multiply accumulate would actually be two operations. And so let's see how many AI tops we have. We want to go through an example in Meteor Lake. But let's look at the formula for it. So we have operations, and we're going to multiply that by the clock frequency. And because this is trillions, we're going to divide it by 10 to the 12. So as I mentioned, operation is a multiply accumulate. So that's 2 times frequency divided by trillions. Let's look at Meteor Lake. We remember Meteor Lake had 11.5 peak tops, right? So on the Meteor Lake NPU, we had 2 neural compute engines. Each neural compute engine, we actually had 2,048 max per cycle. Okay, and a mac per cycle, remember a mac is 2 operations. So we basically have two operations times 4,096, because we have 2 neural compute engines. So 2,048 times 2 is 4,096, and then times 2. We multiply that by the frequency. We divide by 10 to the 12 for trillions, and we get 11.5 tops. But tops aren't the only thing that matters. Neural networks aren't only multiply accumulate. There's a lot of other operations that are in there. So this kind of gives you the maximum performance that you can get from a particular IP. But there's other things that matter. So multiply accumulate is really the matrix operations. So we have convolution operations, matrix multiplication. These are our matrix operations. This is really what we're referring to when we're talking about tops. And we say like the complexity is like n squared. So maybe just to give a feeling for this, let's say you're doing a large language model and you're putting in 100 words. We could say 100 words is your n, so our complexity is 100 squared, so that's like 10,000. But actually vector operations matter a lot as well. So they're less complex, it's only n as compared to n squared, but we do important things like activation functions. So every layer you usually need some activation function. Also softmax, if you saw the last session, TAP was talking about softmax and transformers. This is one of the critical operations. And actually what we found is that we're actually limited by our vector compute in Meteor Lake. So one thing I'm going to talk about is how we dramatically increase the amount of vector compute as well that we have in NPU4, so we can really make use of those tops that we're delivering. So again, it's really the matrix operations, through the convolution, matrix multiplication that are delivering the tops, but vector compute also matters. Okay, let's take a look at what NPU4 looks like. So NPU3 is on the left-hand side. We had two neural compute engines here. I mentioned that we had 2048 max per engine, so it's 4K max total. On NPU4, what we did is we scaled up from 2 neural compute engines to 6 neural compute engines. Same number of max per tile, so we went from 4K max, 4,096 max per total for the 2 tiles, up to 12K max, so that's over 24,000 operations every cycle at ITT. Okay, now let's look at some power and performance curves. So besides the increase in the amount of kind of tops per or max per cycle that we can support, we also increase the frequency. So let's look at a power performance curve. So I've already mentioned that we have 4x the peak performance here. If we look at, here's the NPU3 curve, here's the NPU4 curve. We have 4x the peak performance. But also, power efficiency really matters, especially if we're going to deliver a lot more performance. We need to deliver more power efficiency. NPU is supposed to be a device where you're doing, kind of always on, all day kind of operations. So we need it to be efficient. So we also have 2x the power efficiency. Okay, let's talk about the architecture improvements. So we have, the increased tops. That's kind of obvious by increasing the frequency and increasing the number of neural compute engines, but there's a lot of architecture improvements. So first off, we need more matrix compute that just delivers the raw tops. That's based on increasing the number of tiles. And then we also have, efficiency improvements because we're spending most of the time, or most of our compute cycles doing matrix multiply, convolution. That's really going to the matrix engine. So the efficiency of the matrix compute is really what's dominating our power. So we spend a lot of time improving the efficiency of the matrix compute. But I also mentioned vector performance. Vector performance is important. We actually have a 4x increase in our vector performance relative to our matrix performance. And I'm going to give some examples later on that actually show how that benefits us. Also, bandwidth matters a lot, especially with large language models. Large language models kind of have 2 phases. The first phase is, let's say, like the first token evaluation, and you have like a time to first token kind of metric. That's very compute bound. You have all those input tokens. You need to do compute on all those tokens. You still need to read in the data. I mean, these models are huge. Let's say we have a Llama 2 7 billion model. That's 7 billion parameters. Hopefully we've quantized it to int4 per what Tap was talking about. There's still 3.5 gigabytes of data. So after we generate our first token, every token after that, we only do compute for 1 token. So the compute's pretty low, but we have to read that 3.5 gigabyte of data. So bandwidth is super important. So let's go through each of these in a little more detail. This is just kind of a refresher from what I did last year, but at the high level, we first have a control block in the NPU. It's actually just a little microcontroller. It does things like device management, power management, workload scheduling. We also have an internal MMU. The internal MMU does process address space isolation. So let's say if you have multiple applications running on the device, they each have their own process address space. We have an internal MMU that does address space isolation. You can actually have, theoretically almost infinite number of applications that can submit work to the NPU. They all have their own process address space. They'll all be kind of queued up through, the normal kind of scheduling mechanism in the NPU. Then there's the DMA and the Scratchpad SRAM. We have a software managed cache, the Scratchpad SRAM. It's actually increased on Meteor Lake from 4 megabytes to 9 megabytes. This works in coordination with the DMA engine. Basically how this works is, let's say we have all our weights in DDR. We have a graph compiler. The graph compiler schedules the DMA engine to copy data from DDR into our Scratchpad SRAM. This is also where we keep our intermediate calculations. So let's say we have activations we've computed and they're waiting to be used by the next layer. We'll keep them in here. If they don't fit in here, we'll have the DMA engine copy it out to DDR temporarily till they're needed again or till they can fit again. And then of course the neural compute engines. This is really the heart of the compute, and we'll go into more detail there. So, under the theme of kind of matrix and vector compute, we really have two specialized engines for matrix compute with a MAC array and vector compute. That's the Shave DSP. You can also argue that some of these operations are vector operations as well. Let's say besides matrix multiplication, where a lot of power goes is reading and writing data. So we have this inference pipeline where we have a pipeline of operations that can run in a sequence. So we don't have to go back to the scratchpad SRAM. There's a very typical sequence you have in a neural network where you have, let's say, like a matrix multiplication or convolution, and then you have an activation function. And then because we're supporting mixed precision, let's say floating point and FP16, you might go through the data conversion block. So really going through this standard kind of pipeline of operations, we can avoid extra reads and writes to the scratchpad SRAM, which further saves power. And then, of course, we have the programmable DSPs. I'm going to go into more detail there, but that's our vector engine. So in the inference pipeline, let me just give like another example of what a pipeline of operations would look like. Let's say you want to build like an edge detector. Now, this is going to be like a super simple thing to build, but maybe you have like a, let's say like a car, and you want to do like a lane detector. You need to detect edges. So you're going to build like a convolutional neural network with convolution filters to detect those edges. Those convolutional filters are going to run on the MAC array. So that's going to be the first portion of your inference pipeline. Then you need to go through an activation function. So what an activation function does is you could think of it like a neuron in your brain getting activated. Let's say through the convolutional filters that run on the MAC array, I detect an edge. It goes through the activation function. The activation function will say like, hey, I got activated. There's an edge, or there's no edge that I detected. And then finally, we go through the data conversion. We may quantize back to int8. We may convert to FP16. So that's kind of the sequence of operations that happen in the inference pipeline. So let's go into more details in the MAC array. So the MAC array is supporting both int8 and FP16. This is actually a big advantage. If any of you saw the presentation that TAP was doing earlier, there's a lot of networks that are moving to int8, but not everything's moving to int8. Let's say like classification networks, those typically could be quantized pretty easily to int8. But there are some networks that require higher precision. Let's say if you're doing like image denoising or image super resolution, 8 bits sometimes isn't enough for an image. You actually need FP16. So the advantage in our MAC array and the NPU as a whole, we support both int8 and FP16. In terms of the throughput, I mentioned that we support 2048 max per cycle at int8, and then we support half the rate at FP16. And again, the MAC array is supporting matrix multiplication, convolution. We actually have an internal state machine that can really like execute a whole layer. Let's say a whole convolutional layer. You could execute like millions of operations actually with kind of a single instruction that you give. What this nice little animation is showing is what the MAC array actually looks like. So we have kind of a multiplier or a MAC array tile of 16 by 16 by 8 for int8. So each one of these little cubes is like a multiplier. And what we're doing is we're taking a 16 by 16 by 8 input tile. We're doing multiply, and then we're accumulating over input channels. 8 represents the input channels, and we're outputting a 16 by 16 block. It's the same thing for FP16, except we only have 4 input channels, so we're getting half the throughput. And then the next step in the pipeline is the activation functions. I mentioned this earlier. We support some kind of common activation functions. This one is called ReLU. It stands for rectified linear unit. So now let's go back to the example I was giving. We have like an edge detector. We've done some convolutional filters on it. Now we go into the activation function. We want to see if it got activated. If the input is, in this case, less than 0, it means it didn't get activated. It's going to output a 0. If the input is greater than 0, it means it did get activated, and the output's going to be proportional to the input. The final block is the data conversion block. Now we can support in the NPU INT8 and FP16. You can support any mix, between layers. Some layers may be more sensitive than others. Actually, as Tap was talking about, there's this kind of accuracy-aware post-training quantization. Accuracy-aware means you find layers that are more sensitive or less sensitive. So let's say we go from a less sensitive layer that's in INT8, and the next layer is more sensitive. Through our data conversion block, we can automatically convert to FP16, or we could convert, from FP16 to INT8. So that's kind of like the last step in this kind of continuous cycle of, convolution, mapmul, activation function, data conversion. Okay, let's talk about the Shave DSP. So the DSP is really our vector engine. Now, I mentioned that we found that in some networks on Meteor Lake that we didn't have enough vector compute. And it turned out this is actually these more modern networks like transformers. Transformers actually require a bit more vector compute than what we saw for convolutional neural networks. So we found that we needed to increase the vector compute by 4x. So this gives us, we had like 3x more tiles, right? And now we're going to have 4x the vector compute. So it's going to give us 12x the overall vector performance per cycle. And I'm going to show in an example later how we actually kind of benefit from that in terms of stable diffusion execution. Here's kind of a block diagram of what the DSP looks like. So on the bottom diagram, this is our NPU3 DSP that's in Meteor Lake. It's a VLIW DSP that stands for Very Long Instruction Word. What that means is we can execute multiple operations per cycle. So we actually have like multiple different execution units. We have a vector unit, we have a scalar unit, we have a load store unit, we have a branching unit. So we can execute all of these up to 8 different instructions every cycle. But what we were missing out on is having enough vector compute. So what we did is we scaled up the vector portion of the engine. So we have a vector register, and we have a vector unit. We've scaled those up from 128-bit width up to 512-bit. The other thing is to feed those vector instructions, we really need more bandwidth. So we've also increased the bandwidth, our load store bandwidth. And typically the Shave is running out of the Scratchpad SRAM. So this is our load store bandwidth into the Scratchpad SRAM. So if we look at kind of pictorial of what we had on NPU3, is we had a 28-bit vector size, which means we could execute 8 FP16 operations every cycle. And we've increased this to 512 bits, so we can execute 32 FP16 operations every cycle, or it could be 16 FP32 operations. I'm giving the example of multiplication here, but we support quite a few vector instructions, especially for activation functions. We have some special instructions like tanh, sigmoid, exponentiation that can be used for complex activation functions. So I mentioned that models like large language models can be very bandwidth hungry. On Meteor Lake, we had a 64-byte per cycle interface from the IP to DDR. We couldn't actually fully consume all the bandwidth that we got from DDR. But on NPU4, we've actually doubled that interface. We've gone to 128 bytes per cycle. So we can actually fully consume the bandwidth that's delivered from DDR. So if you're going to run like a large language model, we should see better performance on Lunar Lake, where we can, really read those, billion parameter models as fast as the DDR can supply it. So just in summary, tops are important. That's kind of like a headline number. So we have 4x increase in tops. But vector performance matters, as we're going to see an example coming up for stable diffusion. We need to have enough vector compute, otherwise your tops or your matrix operations can't be fully exercised. And then of course, with this increase in compute and with these models that are very bandwidth hungry, like large language models, we need to increase the bandwidth. So we have 2x the IP bandwidth. Okay, let's shift gears a little bit. We're going to go a little bit to like an application of what we've talked about so far. So just a refresher on transformers. transformers are really fueling the AGI revolution. I would say like before transformers, there were some kind of generative networks, but really none of them took off. But transformers is really revolutionizing all the generative networks that we're seeing. But it actually does a number of things. It'll do classification. So this used to be the job of, let's say, like computer vision networks, CNN networks, but now transformers can do it. We can also do translation. The demo that we saw in the previous section of doing speech to text, that's actually a translation network. So we're using kind of two parts of the encoder and decoder that we're going to talk about in the transformer. And then, of course, generation, ChatGPT, all those kind of LLMs that everyone's familiar with. We also saw this in the last session, but just to review, transformer has basically two portions. There's an encoder and there's a decoder. We could think of the encoder as classification, the decoder is generation. When you use the two together, you get translation. So we're going to go through an example of, what are all these operations? How do they map to the NPU? What improvements do we make in the NPU that are really going to improve the performance of these networks? So let's start to go over the mapping. The first thing I mentioned is transformers actually have a lot more vector operations than what we saw in the past. So here we're highlighting all the operations that map to the DSP. We're going to have the attention layer. The attention layer is a supercritical part of the transformer network. We have add and norm, and we have softmax, which is also one of the bottlenecks that we found and one of the reasons we need this increased vector compute. Of course, most of the operations in a transformer are going to be matrix multiply. Those are going to map to the MAC array. So certain portions in the multi-head attention, and then there's feed forward and linear. Feed forward and linear really just mean matrix multiplication. So let's go through kind of a mapping of the attention block. So the attention block is one of the critical parts of large language models, so they can really understand the context of the words that you're putting in, let's say as a prompt, and figure out how to generate new words based on that. So these operations are in the multi-head attention block, and we're going to see how do these actually map to the NPU. So if we saw the previous session with TAP, there's kind of like three parts of what we do in a multi-head attention block to figure out what's the actual context of a word. And we were seeing an example of chips. We don't know if chips is like a bag of chips, or is it laptop chips, Intel chips, or is it Bark chips. So first we're going to take, let's say, chips, and we're going to find with all the other words in the sentence, how much similarity does it have? So we're going to do this thing called like a similarity dot product, and this is going to be a matrix multiplication. Now, once we found out, what similarity each word has with each other word, then we're going to do like a normalization operation. This normalization operation is going to give basically a probabilistic ranking of these from 0 to 1, where the total distribution adds up to 1. We're going to do this with softmax. So this is going to be our vector operation. Finally, we're going to do an attention score calculation, where we're going to move the chips. If we had Intel chips, we're going to move it more towards the chips direction. And again, this is going to be a matrix multiplication operation. So if we just kind of go through where these things are going to operate, we have this word vector similarity dot product, mapmul. It's going to go to the MAC array. We have this similarity normalization. That's going to be our vector operation, and that's going to go to the DSP. And then finally, we have this attention score calculation, and this is going to, again, go to the MAC array. So now let's see an application of this. So stable diffusion, hopefully everyone is familiar with this network. This is a text-to-image network, and we're going to go through first, look at how this maps to the NPU, and then we're going to give a demo, and we're going to look at the performance, and then we're also going to see what's the power efficiency that we're seeing with NPU4 compared to NPU3. So this network actually has a series of operations. First, you're going to put in a prompt. In this case, it's cute kitten with a pink bow. We're going to go through a transformer. This is an encoder. So that's that kind of top block that we were looking at in the transformer. It's going to create kind of an output vector. And this is going to go into the UNet. The UNet diffusion is going to go start with an image, or let's just say start with all noise, and it's going to start denoising successively. After we do that a number of operations or a number of iterations, we're going to go to an image decoder, and then we're going to get the output. So let's see what that looks like. So first we do the text encoder. Then we're going to go to the UNet. The UNet is going to run multiple steps. In the example we're showing, we're going to actually run through 20 steps. The way it works is each step we do, it actually denoises the image. So you can see as it's going through all these steps, we start with noise and we end up with a cute kitten with a pink bow. Finally, we go into an image decoder and we get the output image after that. And if we look inside this UNet, we have actually a mix. There's convolution operations, but we also have a lot of attention layers. So this is this multi-head attention that I was talking about. And this multi-head attention we found on Meteor Lake was actually a key bottleneck to delivering performance. We actually found we were spending like 50% of the time computing softmax on this. So what I've done here is I've taken an execution trace of Meteor Lake compared to Lunar Lake running the UNet. So this is an execution trace of the entire UNet. What we see here is, on Meteor Lake, we have 2 neural compute engines. This shows the execution trace. We can see what's running on the Mac and what's running on the DSPs. And then the blocks that I've highlighted in yellow over there are actually the attention blocks. So you can say, I'm not highlighting all of them, but you can see a lot of time is spent on that, a lot of the execution time. And then if we go to Lunar Lake, first off, we can see the total execution time is significantly reduced. It's running faster. It's also running on 6 neural compute engines compared to 2. But I've also highlighted in light blue, this is the attention calculation. It's significantly faster. We're seeing up to 9x speed up in terms of the performance. So this really helps us deliver a significant performance increase on transformers. This is transferable to other transformer networks as well. This actually shows kind of a zoom in of the execution trace. One unique thing we have about NPU is we can actually execute things in parallel on different engines. So each shave can run while the Mac array is running. So this is actually showing the multi-head attention block. We're doing operations on the DPU. These are the mapmul operations. We're doing softmax operations on the DSP. Still, the softmax operation is still the bottleneck. So we're still somewhat limited by vector compute in this case. Okay, I think we're going to go to a demo now. So last year at ITT, we gave a demo of stable diffusion running on Meteor Lake. At that point, we hadn't enabled the text encoder or the image decoder running on NPU. So at that time, we actually had the image decoder running on GPU. We had the text prompt running on NPU. This year, we have the text encoder running on the NPU. We're still running the image decoder on the GPU. We're still working on optimizing that network. Closer to launch, we should be having that running on the NPU with equivalent performance. And then this is mixed precision. We have the stable diffusion UNet running at int8. The other 2 networks are running at FP16. So we're going to give a demo. We're going to do like a side-by-side comparison. So we're going to show Meteor Lake running stable diffusion, Lunar Lake running stable diffusion, and then they're going to be running on multiple IPs as shown here. So why don't we switch over to the demo. So I think we're going to start with Meteor Lake first. Meteor Lake is going to be rather slow in generating the image, so we can start on the right-hand side with Meteor Lake. We're going to start generating the image. We're going to be able to see how long it takes in terms of the iterations. If we can pull up like the command window where we can see the output. And then we can also start doing Lunar Lake as well. So we can see the number the number of images, the number of iterations running there, and Meteor Lake is pretty much done. So significantly faster. So we have, I think, 22 seconds running on Meteor Lake and 5.8 seconds running on Lunar Lake. So significantly faster. We're actually still working to improve this. By launch, we expect this to be faster. We're kind of targeting like under 5 seconds or so. So this is still a work in progress, but a significant performance improvement. More peak tops, more bandwidth, more vector compute. All those are really contributing to those performance improvements. So why don't we switch back to the slides, and with these systems, we actually took some data yesterday in terms of the power as well, so we can look at the power comparison. Well, first off, we have the performance comparison. So 20.9 seconds versus 5.8 seconds, that was our execution time. We measured the power on these exact systems yesterday. So we had 9 watts on Meteor Lake and 11.2 watts on Lunar Lake. No surprising that the power is a little bit higher because we're doing it much faster. But if we look at the efficiency ratio, it's significant. I had talked about a 2x efficiency improvement from the IP, but we're actually seeing 2.9x at the platform level. So we have 2.9x less power or less energy, let's say, to generate an image. So it's pretty significant. So now let's summarize. So we know there's a lot of new workloads going to be coming to the PC, so we need to deliver more performance. So with NPU4, we're delivering 48 peak tops of performance with our 6 neural compute engines. But we also know that with all these additional peak tops and workloads, we need to deliver much better efficiency. So we have 2x the efficiency that we're delivering, or in this case, we just saw 2.9x at the platform level. Now, we talked about tops aren't everything. We need the right balance of vector compute and matrix compute. So we've increased the shave 12x in terms of number of kind of vector operations per clock. And of course, large language models and other models require a lot of bandwidth. And we also have this increased compute. So we've improved the bandwidth by 2x. All right, so that summarizes it. Thank you, everyone.